So we'll just record this. So first off, what questions do you have from the last couple of weeks? This is, this is the end of the line, so we need to get some things settled. What are the areas that you're having some questions about? And I can't believe that there aren't any, so. Okay. Right. Okay. When you're calculating, that's the traveling salesman problem. How many ways can you go to 5 different locations? And so the rule of thumb is that on something like that, if you're talking about routes between points, it's the number of points factorial. Remember, factorial is n times n minus 1 times n minus 2, etc., all the way down to 1. Okay, so there are 5 cities. 5 times 4 times 3 times 2 times 1. That's 120. Right. So the rationale is you have 5 different ways to go to begin for the first step. So you've taken out point number 1 at this point. Then there's only 4 different ways to go next. Then you've taken out point number 2. Then 3 different ways. So it's all multiplied together. So you got 5 different ways to start and then 4 different ways. That gives you 20 for those first 2. And it goes down until you get down to just 1. Okay, does that make more sense? Okay, well, just the rule of thumb is when you have a series of choices and it doesn't really matter which order you go in, that it's the number of choices factorial. And your calculator on your phone, at least on my phone, does have a factorial function. So if you get a number that's real big, like 11 factorial, you just plug it into your calculator and it'll give you the number of choices. Okay. So, you can do that, or we'll go through a couple of problems and show how that works out. Okay. So is that a little bit easier? Okay, we've got some formulas that we have to follow. And what I would urge you to, if a formula doesn't make sense, let's talk about it and see if we can find a way to help you understand why it makes sense. Okay. Exclamation point, yeah. Right. Well, that's why again, in the book, it talks about how you solve these problems. And so the question was really, how do you solve this problem? Okay. So that's the examples that we've given in the book help us with that process. You have a question, Brandy? Okay. Provide a written description of the if we have, okay, let's just take a look at the room here. If we include me as part of the class, we have 3 men and 2 women. Okay, so the number of men is 3. The number of not men, the complement is whatever is not what your criteria is. So the number of not men is 2. Okay, so the complement. In the same way, the number of women is 2. The number of not women is 3. Okay, so in a case of, and this is definitional, we talked about this last week. In the case of at least 1, the complement, the only complement that makes sense is none. Okay, at least 1 means that it could be anywhere from 1 to all of the sample, right? So the only complement to that, the only way that is not at least 1 has to be 0. Okay, does that make sense? Yeah. All right, it is maybe first time I ran into that, I thought, that doesn't make sense. And then I thought about it a little bit, and that's how I came up with it. Okay, if it's at least 1, then the only way you can have not at least 1 is none. And that's the logic behind that kind of a question. Okay. Okay, other questions? Yeah. Does it make more sense now, Richard?
Yeah.
Good. Good.
And I understood the company. Just claiming that, you have to.
Right, yeah.
They don't know.
Yeah, you don't know. Yeah, at least 1 doesn't rule out everyone. So that's the logic there. So what else? Okay, let's take a look at number 9. And I may go up to the board to work on this. A batch consists of 12 defective coils and 88 good ones. Okay, that tells us the batch size. Okay, so one of the things we have to do is look at what N, number N is the number of items in the sample, right? N has to be 100. Find the probability of getting 2 good coils when 2 coils are randomly selected if the first selection is replaced before the second is made. Okay, so when we take 1 out of this 100, it has, since there are 88 good ones out of 100, that means there is an 88 out of 100 probability of getting a good one. That's 88%, or 0.88. Okay, if we then replace it with a random coil and then pull out another random coil, then there's still 100 in the sample size, right? So then it's, again, 88%. So we have 0.88 times 0.88, which is 180. Pull out the old calculator. Again, in math classes, calculators are critical. 0.88 times 0.88 equals 0.774. So you made the right choice. Now let's throw in a wrinkle. And again, this is how statisticians think. If if each of your batches, each possibility of 100 coils is going to have 12 defective coils, then there is a 12% chance that the coil that you put in is really defective. And so now we would have 13 defective or 87 good coils. And then it would be, if that were the case, 0.88 times 0.87. Now, what we want to do is but modify that slightly, and the statistician would do this. What is the chance that the other one is going to actually be a defective coil that goes in? So there's a 12% chance that it will be defective. So we have to reduce the probability by that potential. Now, we haven't gone to that level here, because we'll assume that it's replaced and it still has the same probability. But it could easily be that way. And in fact, if we do 0.88 times 0.87, we get 0.7656. Well, guess what? That's not even a choice. Okay? So the only way to estimate that is to estimate the probability that we would have 0.8, that it would actually come in as a defective coil. So that's going to be actually 88% of 88%. So there's a chance, there's a chance that the second coil is going to be going in is actually going to be defective. So, we're not going to go to that level, but this is how I would look at that. Are there more? The problem with statistics is there's always another level you can go. And in this case, I think that 0.7733 modified doesn't actually, you can't get to that number. So this one obviously has made that number. But statistically, if you were doing a very sophisticated statistical analysis, you would take into you take into account the probability that the next one is actually effective. Okay. And so the probability of getting two good coils actually would go down a smidgen. So, and smidgen is not exactly a rigorous scientific term. Okay, since my phone was buzzing me before I picked it up, I just wanted to warn you about something. I had an interesting conversation last week with a woman, because I got a phone call from a supposedly Denver number, a 720 number. And this phone, I've been getting a phone call from this number regularly for the last week. Since I don't know the number, I ignore it. I finally got tired of the phone ringing, called the number, and this woman answers, "Hello?" And right away I knew something was wrong, because if it was a business, it would have sounded different. So I said, "I just got a phone call from this number because it is just wrong." She said, "Well, I didn't call you." She sounded kind of suspicious, and I thought, "Yeah, you think I'm trying to do something here?" I said, "Well, no." And I said, "Okay, I've had calls from this number at least 6 times in the last 2 years." And she said, "Well, I haven't called you." And I said, I suggest you talk to your carrier. Somebody's hijacking you. Somebody's pretending to be you. And you don't want to start getting phone calls like this from people who might not be as polite as that. And at that point, she's, oh, well, okay. And I said, sorry I bothered you. I won't call you again if I get a call from this number, but check with your carrier. Well, the phone just rang, and it was the same area code, the same exchange, first three digits, but a different way. And I thought, yeah, what it is.
I get calls from my with the phone number 0993 and then random last number.
Yeah, that's part of the scam. They're trying to get you to answer because most of us, if it's a business number, we're not going to call it. And the real key is when they don't leave a message. At that point, I know. And these are people trying to offer me lower rates than my credit card. And I keep trying. I've tried several times to talk with them, but I never can actually call them and get them to call me because I want to tell them, oh, are you going to pay me with my credit card? My current interest rate is 0 because I pay off my card every month. I'd be happy to have you pay me your card. But no, they won't do it. But so be aware that can happen, and it seems to be happening more. I'm getting constant calls. Oh, I hang up. Yeah. They either answer immediately. I'll give them a second because sometimes, somebody's taking a breath, they're just following, or, something. I'll give them a second, but, usually it takes 2 or 3 seconds for the computer to buzz through. Because a lot of times, as I'm clicking it off, I'll hear, oh, yeah, like it's gone. So, yeah. But, and my phone's on a no-call list. So, pardon? Oh, yeah, they still keep calling. Because nobody enforces the list anymore. The government doesn't make it enforce the list. And with our current Federal Communications Commission, ain't going to happen anytime soon. So, I don't figure people have a right to make money off me. Okay, other questions? Richard, you're working on something. You have a problem? Yeah. Yeah. Well, again, what we're trying to do is make things a little more sensible, sound a little bit more like they make sense, because we are surrounded by statistics. I mean, we hear them all the time. And what we need to be always doing is saying, what is this? And how do people misuse statistics? I can't remember where in the book, there's something called looking at correlations. I want to talk about that a little bit first. A lot of times we'll see people trying to say, well, okay, is there a correlation between two different things? The example in your book was a correlation in New York of the price of a slice of pizza and subway fares. Okay, this would seem to be completely unrelated. Why would the slice of pizza, the price of a slice of pizza, and the price of subway fares be related in the slightest? But if you plot the data over time, the increase in the price of a slice of pizza, and you look at it at the same time as the increase in the subway fares, they're right on top of each other. So does that mean the price of pizza causes subway fares to go up? Or does that mean that subway fares cause the price of pizza to go up, or are they completely unrelated? And the problem with this is we have an appearance of a relationship. Things can be correlated. In other words, two things can happen at the same time and look like they have a relationship when they don't, or when the relationship is something else. In this particular case, in your book, they go through an analysis of also looking at the consumer price index. And if you look at the consumer price index, that's predictive of increases in the price of a slice of pizza and increases in subway fares in New York. So the consumer price index seems to be the thing that drives this. Is it a cause? We tend to try to make things look like, because they sort of follow each other, it's a cause. Okay? But it's not necessarily. Sometimes it is. Does the consumer price index cause the price of pizza to go up? Well, there's a real interesting question, because how do we calculate the consumer price index? We calculate it by the increase in prices of a basket of goods. So chicken or egg, the CPI doesn't cause things to go up. Price increases cause the CPI as a measure of those price increases to change. So we need to be careful when we look at this. Primary example in medicine is the correlation between children getting vaccinated and the appearance of autism. This has been a controversy in the vaccine field for a long time. And if you look at it and you talk to parents who have to deal with autistic children, and some autistic children are, mild and relatively easy to deal with, and some are unbelievably difficult. So I have a lot of sympathy for parents that have to deal with an autistic child. However, if we look at the age of onset of autism, it happens to be at a time, an approximate age, when a round of a series of vaccinations is being given. So the original work that led to this hypothesis that vaccines cause autism came from a gastroenterologist who was studying the relationship between was actually studying autistic children, and he correlated this in a series of children as something that happened right after vaccination. And you hear lots of stories of parents who say, I took my child in for a vaccination and they were never the same again. Very complex question. Emotional issues, some scientific issues, and medical issues as well need to be looked at. In this particular case, if we look at autism in general, generally speaking, it shows up around age 2 in our children, if they're going to be autistic. Generally speaking, I mean, everybody's different. So again, that's a statistical average, right? So generally speaking, it shows up about then. And at that time, they're getting their vaccinations. And it's not like they get vaccines and all of a sudden, instantaneously, they go blur, completely berserk. But it is something that parents notice happen after after a vaccination. It was blamed on a lot of things. The problem is we had either 6 or 9 patients that this guy examined and made this claim. Well, 6 or 9 patients is not a statistically valid sample. It would be something that if it were published about anything else, it would be an observation. Maybe this is something we should look at. Okay, that's a valid observation. But to say that it causes autism is a different story. So sophisticated, again, the problem with this is it really took hold. Parents wanted something to blame for their children being autistic. And we're real good at blame in our society, in human society. So parents wanted to blame something, so they blamed the vaccination. As I said, it's perfectly legitimate to ask the question, could there be a relationship? Or is this just a correlated activity, correlated event? And so after a lot of analysis, first off of larger samples, a lot of it retrospective. A lot of it came out of the huge database that is maintained by the Danish government for Danish students, and also a huge database maintained by the Japanese government. The blame for the vaccine was the MMR. We've all had it, measles, mumps, rubella vaccine. Well, I didn't have it. I got measles, mumps, and rubella as a kid. But nowadays, everybody gets this vaccine. And so that was part of the blame. Statistical analysis showed that there was no correlation between the two, between autism and MMR. So then the blame shifted to the preservative, which was thimerosal, which is a mercury-containing preservative. And so the blame was shifted to mercury. Well, statistical analysis of mercury or thimerosal-containing vaccines versus the same vaccine without that preservative showed absolutely no correlation at all. In other words, there was no difference in the rate of autism on the thimerosal versus non-thimerosal containing vaccine. To further complicate the measure, the Japanese database, in Japan, they don't give triple vaccination, they separate them. So what they found in Japan was the data from before they separated the vaccines, there was a rate of autism. When they separated them and started giving 3 different vaccines, the rate actually went up. So it's not the triple combination. So the data don't support it. That does not mean that we don't still have that controversy. There are still people who will swear to you that autism is caused by vaccination. So again, what is the correlation? Well, we're learning a lot more about the relationship between the bacteria in our gut and our health. And so what we're seeing is what the guy that did the original measurements, he was actually on the right path, I think, in that what he was looking at was the inflammatory response, inflammatory bowel disease in these children. That's what it got him into looking at these things in the first place. He was looking at the relationship, and he was finding that what we now know is that there is a definite increase in autism rates in children who have various forms of inflammatory bowel disease. versus populations of children that do not by some measurement. I don't know how it's done. But those are data now that have come through. So the guy that came up with the first hypothesis blamed the wrong culprit. But that hasn't stopped people from blaming vaccines. So one of the things that the lesson here for me is that there is we call it a meme. You know the term meme? Okay, the meme of vaccination causes autism is more important than the scientific data that says there really isn't any correlation. And that has caused a lot of problems. So this is, again, where statistics can help us understand an issue. Doesn't mean that people are going to buy it, but it means we can understand the issue. And, we can set aside, the vast array of statistics that show us that the prevalence of various childhood diseases is reduced by vaccination. And we know we can eliminate diseases. We've done it with smallpox. We are getting closer and closer to doing it with polio by the simple method of vaccination. So there are places where we have to look at that, the data. We have to ask ourselves, are we making the right assumptions? As I said, the price of pizza does not drive the price of a subway fare. The price of pizza is related more, and subway fares are both related to consumer price index. But we need not to move into causation, because the consumer price index is just a measure of inflation. And so what causes the rise in price of pizza and the rise in subway fare in New York? Inflation. So we can show these things. That's what really regression analysis is supposed to tell us. Is there a relationship between these two? And again, just because there is a similar pattern does not mean that there is causation. Okay. Does that make sense? So we're not going to go much further with this, the idea of doing a regression analysis. There's all sorts of calculations you can do. But the calculations really come out to what is the likelihood that these two are correlated. And it's not intuitive. The pizza and subway fares are not intuitively correlated in anyone's mind. I mean, when I first saw the problem, I thought, well, this is kind of bonkers. And I knew where they were going, because just because they both follow the same trend doesn't mean they cause each other. It really is. And with things like even the consumer price index is a measure only of other forces. So the CPI increase doesn't cause increases in things and prices, but increases in prices are measured by the consumer price index. So again, we have to be very, very careful. You could look at the April, in your case, you could look at how many tubes of toothpaste you put in your room as a cause of the room being rented, because the toothpaste doesn't get used unless the room is rented. And even then, it's not necessarily used, but people might take it anyway. But they're convenient. They're really nice. And if you travel a lot, it gets you around TSA crap, right? Okay, so that was Yeah, yeah, yeah. Yeah, usually that's the thing that people don't carry. But the other part of that is you could, again, you could measure, you could look at the replacement rate of shampoo and conditioner, because some people will take the half used and some people will not, and you can't leave a half used anything in a room for the next client. Yeah, they have to be. So you could use that as a measure of occupancy. You could correlate the number of tubes or bottles of shampoo or bars of soap and use that as a measure of occupancy. They're correlated. Are they causative? Well, yeah, in a way, in this case, because they wouldn't be used if there weren't people in the room using them, right? So you could say that these are actually causally related. The occupancy of the room is driving the usage of these amenities. But you could also go back to the amenities and relate it exactly and directly to the room. But the use of amenities doesn't mean that it doesn't drive the use of the room. It's the other way around, right? So you can correlate these things. And in your case, there is a direct relationship. But, you can't say that shampoo drives room rental. Nobody rents a room because of the shampoo. Now there is another one, you can look at that. Yeah. Ooh, what a bad choice.
I don't know who decided that would be a good week. But, amazing. That's what it lasted. We had just about every room for full family.
Just for the pool.
Yeah, and they live in making pool. And this year, we weren't gonna have.
So are you letting people know when they make a reservation that the pool isn't going to be available at those times, or are you going to have angry customers? Yeah.
Right now.
So at certain times, you can say that the presence of a pool is influencing the room rate. Does it actually cause it? Well, in some cases, if people are making the choice because there's a pool, then you might be able to make that argument, but you can correlate it. And, this year during spring break, if you track that and compare it to last year, you can go back to your corporate management and say, this was a really bonkers idea. Don't do it elsewhere. Yeah. Ooh.
Luckily, the majority of people on the yesterday, but I had 2 people come and they're after midnight who are very tired. Other ones, therefore, they had asked us to walk down the hallways and take the stairs. And luckily one of them, their room is right at the front of the stairs. The other one, the room is right across.
Well, yeah, that, yeah, elevator maintenance is kind of critical. But you would think that they would pick a weekend or something when you'd have lower occupancy. Okay, a time then of lower occupancy.
Yeah.
Oh.
But I think we were originally were going to take care of the elevator last month with January.
Yeah, for most people it is, yeah.
But they hadn't quite gotten the second floor started. And last week, they're like, oh, yeah, the second floor in the break room. That didn't happen. I don't know what's going on with the second floor.
Haven't done it yet. Okay, so let's take a break, our first break. And we'll come back and go on to some other topics. But I just wanted to really go through the idea of correlation and how you things can be correlated, but not related in a causal way. Because there's lots of things we can look at, lots of, and the pizza Subway thing is kind of is a real issue. I mean, these are solid data. They are definitely correlated. So what is, and people are bad about thinking, well, this happened, therefore it caused by that. That's the whole vaccine thing. My kid got autism after a vaccination, therefore the vaccination caused it. There is absolutely no support for that scientifically, but you can't argue with a parent about that particular emotional issue, nor should you. You won't get anywhere. But you need to understand that education alone is the only way you can get around these issues. It's definitely chicken and egg stuff. Uh-huh. I'm going to resume the recording. We're going to talk about normal distribution and how we use it. There are lots of variations. The chapter has quite a few sections. We won't be covering every section. Okay. Okay. I like writing on the board. You don't know how to work Excel? You don't remember from Act 101? Okay. Um, well, let me see if I can pull that up then. And we'll see if we can make that work.
This week's in chapter 6.
Yeah. Okay. So let's, now which one are you looking at? Assignment 4. So let's pull up, let's go ahead and okay. Let's go up and go ahead and pull that up. Let's see. On that now, so we'll have to see what we project on the wall here. Let's throw the lights. We'll try just using the whiteboard. See if we can't. Ah, it works. Good. Got my mug up there. Let's see, I want to, let's pull up Excel. And let's create a new worksheet. Okay. And then let's go back here and share the screen. All right, that work? Okay, so read the assignment. Mm-hmm. Right.
Properly label your data. Create a bar graph using your data label. Create your bar graph, add error bars using your standard deviation calculation. And then it gives us the 3 sets of data.
Right. So one thing you have to remember, let's look at the formulas that we have a choice of. And we have, note here, we have math and trig. And we have, let's see. Okay, so more functions, statistical functions. So under more functions, we have statistical. Here we have the ability to calculate the median, the average, okay? Average and mean, remember, are the same thing. We have the ability to calculate the average. So let's put in a some of the data. What are the data? Okay. Okay. Let's just do the first one for now. Okay. There's several things we can do with this using Excel. This is our data set. If we highlight the data set, which you do by, clicking on one and just dragging through the rest of the data set, we can manipulate the data. If we go to the Data tab, we can sort. If we click on Sort, then we're going to sort column A and sort on the values, and we can set the order. We can sort on values, we can color, etc. We have lots of choices, smallest to largest, largest to smallest, or some sort of custom list. In this case, we're going to want smallest to largest. If we click OK, the data now are sorted. Right? So they're now in order. So we have, in this particular case, we have a mode of 7, the most common value, right? Now we've got 10 values. So the median is going to be midway between 13 and 6. So let's go over here and actually go back to our formulas, go to more functions, statistical, let's do an average. Okay, the range is going to be, we have to figure this out. We want the range being A1 to A10. Okay. All right. This returns the arithmetic mean of these arguments. Okay. So if we click OK, we get 15.6. Okay. So we can use this for our data set, right? All right. So let's look at, we can also go here to the median. Let's go down to median. And again, the median is going to be of the same range, A1 to A10. Click OK. So now we have a mean and a median. Okay. They're not the same. In fact, they're, to me, significantly different. Okay. So if we now look, go down to a different place, and we look for the standard deviation. Okay. And we have two choices, the standard deviation of a population or the standard deviation of a sample. So we're going to use the sample standard deviation. So we've got, the first number is going to be A1. Number 2 is going to be A2. And we can keep on going. Okay. Number 3 is A3. And we can keep typing these in. A4, A5, Okay. A6, A7, A8, and we can keep on adding as many as we need. A9 and A10. Now, note that we could also just put in values. All right. So now we want to know what the standard deviation is. Standard deviation is 8.2. All right. Makes sense? Okay. Variance is simply the square, right, of the standard deviation. So you can easily calculate that. We could also go back through and look and see if there is a variance calculation. Probably there is. Variance of a sample and variance of a population. Okay. So you'll see that that is done. That makes sense? So this is how you use formulas, at least in statistics, but it's also how you use formulas in Excel in general. Right? Is that some of this coming back to you from EPS 101? Yeah, I thought it would. Now, what was the other thing we're supposed to do? We're supposed to plot the data, right? Supposed to do a graph, right? Is that right? Okay, let's just see data. I can't remember exactly where. Let's do a bar graph. All right. Let's see. I can't. This is a different version of Excel than the one I am used to using. Okay, data. It's an insert. Okay. Insert. Okay. People graph. Okay. So we have inserting tables. We've got statistical charts. We've got bar graph. So we're going to click on bar graph. And then we have a choice. We can have a vertical or we can have a horizontal. We can have two-dimensional or we can have three-dimensional. My preference is to keep it simple. So always use two-dimensional. Three-dimensional tends to be a little more confusing to look at. So we've got 2D columns and, all right, selecting the data. Our data range for the chart is again next page, A1 to A10, okay? All right, that's not working. Selecting the data, okay? So we select the data by highlighting rather, and just and choosing the data column, right? So we want the data. So now we have a chart. We can put a title on it. So this shows the data, the values of the data for each of the data points, right? Make sense? Okay, we go to the Insert tab. And you'll note over here under Charts, we've got lots of choices. We can look at the different kinds of choices, okay? But we have lots of choices. We can create a pie chart. Not that that is going to give us any more information than we have. But we have a variety of different things to choose from. Okay? That making a little more sense? And what else are we supposed to do with these data? We're supposed to create a bar chart, right? Yep, we can label it. We're supposed to add error bars. Well, in this particular case, we don't have data ranges. Okay. So what we have is what else? What other charts were we supposed to look at? Were we supposed to look at? Okay. Yeah. Well, we've got, we know how to do the variance. We know how to do mean and median. We know what the mode is. That's easy to see from the order of the data. Okay. So we're supposed to, what kind of plot were we supposed to use? Create a bar graph. Let's see. We need to look at. Let's see. No, that's not what I wanted. Okay, we had a column. And we can give it colors if we want. We're going to leave it there. Let's see, I'm trying to find the statistical charts. Sorry? The middle one? Okay. So what we have is error bars. Okay. Error bars are, let's change the color of this if we can. See it a little bit more. So we have here we're focused on the median. And we have the error bar that is for the data that ranges from, obviously we can't, our error bar cannot go below the lowest data point. But remember, the error bar is related to the standard deviation. And what we're seeing is the bulk of the data. If we look at this, the bulk of the data are in that box. Okay. If we look at some of the other statistical, oops, it doesn't like that. All right, let's go back. Okay, and insert statistical. Okay. Okay. So we have our error bar here. I mean, it's a case of choosing the right display. All right, does that make sense? For this little bitty bit of data, this is kind of useless, but it's what they want you to do is get practice using Excel, because it's a really powerful tool with all the formulas and everything else that we have available to us. Okay. Okay. Let's go back here. I'd like to look some more. Okay. Does that help?
Yeah.
Okay. All right. So I'm going to get back out of this. And we're going to then disconnect.
So is that because some of the bar graphs is data and value.
Yeah. Yep. The mean is what we need for calculating the standard deviation, right? So I'm going to turn the lights back on. Okay, that ought to shut off now. Okay, does that help? All right, let's talk about normal distribution. I'm just going to get started on that and take our second break. But a normal distribution is one where you have enough data where you can have a fairly smooth distribution of data. The mean of a normal distribution is the maximum point on the curve, the apex, right? So that's the mean. And then we have the standard deviation. Okay, so this is one standard deviation minus one. But around the mean, there is a negative sign and a positive sign, because when we measure standard deviations, they're either negative or positive from the mean. So we have -2 standard deviations, +1 standard deviation, or +2 standard deviations. And remember that 95% of the data falls between -2 standard deviations and +2 standard deviations. So anything that falls outside of the standard deviations, the 2 standard deviations, considered to be an unusual value in a measurement. So anything that is more than 2 standard deviations away from the mean is considered to be an unusual value. So if you're measuring, for instance, the amount of toothpaste in a tube, and the tube itself lists the size as, let's just call it 10 ounces, a big tube of toothpaste, right? When the company that manufactures that tube of toothpaste does its quality control analysis, it does so by weighing a tube or a series of tubes and relating that, subtracting out the actual weight of the tube itself to get the entire contents. So if we're supposed to have 10 ounces, that means that if we have a large batch, the mean of the filling ought to be 10 ounces. Okay. Now, if let's just say that our standard deviation from that is 1/10 of an ounce. Okay. So anything within 9.8 to 10.2 ounces would be considered normal. Do you have that kind of variation? Probably not even that much, but this is just an example. But if we had, instead of 9.8, if we had 9.78, that would be outside of, that would be more than 2 standard deviations below the norm and would be considered an unusual event. Right? It would not be considered expected. So when you had something like that, your question would be, why? Why is something falling into the unexpected range? If you were running a QA operation at Colgate and your 10-ounce tubes started coming out with a high number of 9.78-ounce tubes, your question would be, what's going on? What's wrong with the filling process? So we use it as a way to monitor. The same thing is done in clinical, in the medical field. If you have a drug and you're supposed to have 100 milligrams of drug in the tablet, we have a process for manufacturing it such that there will be a mean of 100 milligrams. Now, whatever the drug is, say the standard deviation is 1/10 of a milligram. That means that if you have anything between 99.8 and 100.2 milligrams of drug would fall into your normal range. Anything outside that range would be considered unusual. And your first question would be, what's going on in the process? So we use statistics in our QA process, whether it's for toothpaste or drugs, to determine you know, what's going on. Automobile manufacturing. We may be looking at a car coming off the line, and we're looking in our QA of our manufacturing line. We may look at some set of parameters for defects. Might be performance of engine, might be defects in the front end alignment of the cars coming off the manufacturing line, might be any number of different things. But we'd measure those and we would have a range. And that range would be plus or minus 2 standard deviations from our goal of our mean. How do we establish that? We establish it by looking at the manufacturing process and at the end result. What is it we want to see? What is our expected range of performance of any product or any manufacturing process? So we use these things as a means of coming up with control of our manufacturing processes. We also, in the say your industry, April, the hotel industry, we look at occupancies on Wednesday nights, okay, in our room. And we know what our general range is. We know what our mean is. We can do that by taking any amount of our data and doing, figuring the means of, the mean for the data. So we know, let's just say that our general occupancy on a Wednesday night is 70%. Just pick a number random. I have no idea if that's reasonable or not. I don't know enough about the hotel industry. So let's just say it's 70% occupancy. And let's say that all of a sudden we have, we're measuring it, we find a Wednesday where it was 30%, way outside our standard range. Let's just say that our average is 70%, our standard deviation might be 5%. So anywhere from 60 to 80% would be our expected range for a Wednesday. And all of a sudden we have 30%, way outside of our 2 standard deviations. Again, the answer is what's going on? Well, in your case, it might be, well, there was a bad snowstorm and nobody was on the road or something like that. But we are looking, the purpose of looking at these things is to look at the probabilities of an event occurring based on expectation. Okay. Gambling establishments do this all the time. They look very closely at the payout rates. Do they fluctuate? A little bit. I mean, they have to, because theoretically it's all random. But what they do is they watch for the payout rates on, say, a slot machine. And if suddenly the payout rate goes up, they start to wonder what's going on. What's with the machine? Is it broken? Is that possible? Absolutely. So that's how they watch these things very, very carefully from a statistical standpoint. Okay. Okay. What's going on here? Oh, stop share. There we go. All right. So let's then, how do we use this? I mean, this is all well and good, but how do we use this? If we're given a set of data, how do we calculate a probability? And the probability is based on what we call a normalized distribution. If we draw a curve here, and we've got here the mean. If we set that at 0, because we've got plus on one side and minus on the other, the area, what we call the area under the curve, which is everything here out to as far as it goes in either direction, area equals 1. Okay, we just set that. Okay, around a mean of 0. Okay, so our standard deviations are going to be some, again, looking at our data. Remember, our standard deviation is that 66% of the data fall between 68% of the data fall between -1 standard deviation and +1 standard deviation. So that means that we can relate the area here. That means that the area between between +1 and -1 standard deviation is 66% of the area, or 68% of the area. So what we expect is that 68% of the data are going to fall in that range. Now, how do we use this to calculate something, what percent of the data are going to fall at an extreme? Or how much of the data will fall above or below a certain value? And that's done by relating this area here, and your book does this reasonably well. At this point, it might be useful to have to go ahead and pull up so I'm going to go ahead and do that. Where is it? All right. All right, so let's go ahead and pull up on your computer the Chapter 6 PowerPoint, which you should have access to. If you don't, let me know, please. Okay, so I'm going to pull that up. A couple of things. There is a the concept here is that looking at these graphs, they are bell-shaped, the standard bell curve, and the mean is 0, standard deviation is 1. I'm talking about the slides. We're going to assume also that the data set is large enough that we have a continuous and uniform distribution of values that spread across the range. A data set that is large enough theoretically will produce a bell curve. Small data sets give us skewed graphs because they're more influenced by extremes, often extremes at one end rather than both ends. A large enough data set will have extremes, both positive and negative. Okay. If we look at something called a uniform distribution, meaning basically the same level at all times, you can see that if we look at the data, we can immediately relate a box plot like this, a uniform plot where we have a standard area. We can relate the shaded area to a percentage of the total. That's pretty easy to see. But a normal distribution is not a box. It's a bell curve. We can use the same principles if we look down here at the next slide, slide 12, that if we define, and this is definitional, if we define the area under the curve as 1, the total area, then we can shade a part of that area and use that to calculate the probability of a data point appearing in that range. All right, now how do we do that? Well, the easiest way is to compare it to, remember the number of standard deviations that a data point is away from the mean is called the z-score. So something with a z-score of 0 is exactly at the mean. Something with a z-score of -1 is -1 standard deviation from the mean, etc. Okay? So what we have is the ability to use that. We used table A2, which is, as I said, the easiest way to get it is it's in the back cover of your book. Okay? And A2 relates z-score to probability, to area. Yeah, that thing. Yeah. Yours came out, but yeah. 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 Okay. There are other methods. We're not going to go into that. We can use Excel. We can use various other software forms. We can use I think StatDisk is your text disk in the shell as part of it. Some of you may actually have the disk. Yeah, some of you may have the disk. And then you can always use the TI calculators. Okay. So I use table A2. That's what we will be using in this class, table A2, because we're not going to go into the use of that. So if you take a look at this slide 15, you'll see that if we look at this value, and the z there is just a z-score, whatever it is. Okay, so the cumulative area to the left of that vertical line at z is the probability of a data point falling into that range. Pardon? Yeah, it's very large. Yeah, you've got a great big portion of the range. And what we know is that the majority of the data are going to fall between, the vast majority of the data are going to fall between plus and minus 2, a z-score of -2 to +2. Anything outside of that is unusual. So we often will look at what is the probability of an event occurring outside of a standard deviation of +2. So larger than, with a z-score of larger. Let's go to the table A2. In the back of your, I'm using the one in the back of the book. You can use the pull-out stuff that Richard has there, or you can go to the tables in the appendix. But since we're working with these, we'll just use the one in the back of the book. So what we have is we have 2 pages. One is negative z-scores. Obviously, you've got around 0. And the other is positive z-scores. In other words, to the right of the mean. So if we look at anything above 2.0, and in this case, we're looking at this number that's in the table is the area of the curve, the proportion of the area of the curve to the left of the z-score. So we have a z of 2.0. It's telling us that 97.72% of the data will fall to the left of a z-score of +2. That includes all the data to the left of z-score -2. So that includes all the improbable data as well as the probable data. Also look at this table. We have these columns. So we have a z-score of 2.01, which is outside of our limit and is going to be considered an unusual score. But there, 0.9778 of the data fall to the left. So we can also take this another level. In between a z-score of 2.01 or 2.01 and 2.02. So we can take this to one more decimal place by a process we call intercalation. So what is the probability of a data point at 2.012 z-score? And so what we do is we look at the difference between 0.9778 and 0.9783, and we come up with a difference of 0.0005. And what we're asking is we want to go to, we said 2.12 as our z-score. So that is 2.12 is 1/5 of the range is between the 2 points. The range is 5. So now 2.12 would have a probability of 0.9779. Intercalation is merely the ratio of the difference in the z-scores to the difference in the probability scores. As I said, the probability score here was 0.0005. That's the difference between 9778 and 9783. And we are going from 0.01 to 0.012, which is 0.4 of the difference, right? No, 0.2 of the difference, 0.2 of the difference between 0.01 and 0.02 would be 0.012. So we then multiply 0.2 times the range difference between the two. 0.2 times 5 is 1. So we'd add 1 to the 2.01, to get a probability of 0.9779. That makes sense? So intercalation is something we do a lot in math, especially using tables. That's automatically done for you in some of the software that's used, MinTab or StatDisk or whatever, okay? Or on the TI calculator. But we're going to do all this, manually. Okay, is this making sense? Okay, so really the issue is that z-scores tell us the likelihood of a piece of data occurring in a range defined by z-score. Okay. Now, there's a couple of things. Anything with a z-score of above +3.5 or below -3.5 is considered a probability of 99.99%. Okay, all data, 99.99% of data will fall between -3.5 standard deviations and +3.5 standard deviations. So if you had a z-score from your calculation of, say, 6, we just assume that it's 99.99% of the data. There is no such thing as 100% of the data falling below or above a certain point, because the point itself is excluded. So 100% is an impossibility. It's like the percentile. You can't get above 99th percentile because that's where you are. You are at that top number. Make sense? Okay. So that's how we use this table. Okay. So let's go through. Pardon? Are we late? Oh my goodness. Please let me know. Yeah. Okay. We know that the standard deviation is 15. So if we are looking at if we go to page 272 in your text, problem number 5, we want to know the probability or the percentage of adults with an IQ below 120. So what we have is, if the standard deviation is 15, the thing we have to do is calculate a z-score. If the standard deviation is 15, then the way we calculate the z-score is the value that we are interested in, 120, minus the mean, which is by definition in IQs 100. So that's 20. 120 minus 100 divided by the standard deviation. So we have 20 divided by 15, which is 1.333, etc. Right? Make sense? So to find that percentage of adults that is below 120, we go to a z-score of positive, considering that it's to the right of the mean, so it's positive, of 1.33. And we're just going to leave it at 1.33. So we read down table A2 to a positive 1.3, read across to the column that is 0.03, that gives us 1.33, 90.82% of adults are going to be at 120 or below as an IQ. Now, what about above? Well, above is the difference between the total area, which is 1, and the probability we just calculated. So the difference between 1 and 9.82 is going to be 0.0918 if we subtract 1 from that. Okay? 0.0918. That means that 9.18% of the population will have an IQ above 120. That's if you believe IQs. I'm not sure I do because of the way they're measured, but that's neither here nor there. People use this. Actually, IQ was developed for the United States Army in World War I so that they could assess the potential mental ability of the draftees going in so that they could assign them to various different tasks. Okay, that was how this whole IQ thing came up, and it's been used and abused ever since. Okay. I get amused when someone says to me, well, I have an IQ of 160. When was it measured? Well, when I was in 4th grade, and this is a person my age. Well, that's meaningless today. In 4th grade, okay, he was a smart kid. He had a high IQ as measured by what he knew versus what the average kid knew. And it's interesting, different groups are viewed as having higher or lower average IQs. And it turns out on close inspection that it's nonsense. It depends on how you test it. So anyway, let's take a look at number 7, which gives us a different perspective here. What we're being asked here is to determine the proportion of people. If you just took a random person, the probability that their IQ would be between 90 and 115. Okay? If we look at these two at this plot, we have the area, shaded area, is between 90 and 115. So what we want to do, the way we calculate that area, is figure out what the area would be if we were just looking at everyone at below 115, and then subtract from that area the proportion below 90. Now remember that we first have to calculate a z-score. 115 minus 100 is 15 divided by 15. So the z-score on the right is +1. So if we go back to our table and we look at plus 1.0, we get 0.8413. So 84.13% of adults will have an IQ below 115. Okay. If we look over here at the 90, we've got 100. We have 90 minus 100 is minus 10. We know this is supposed to be negative because it's to the left of the center point of the plot. Okay? So minus 10 divided by 15 is going to be 0.666. We'll round it off to 0.6. We'll round it off to 0.66. Well, it should 6666. So we're going to round it off to 0.67 just because. So we look on the table for the minus scores in Z, and we go to minus 0.6 and read across to the column 7. So we've got 0.2514. So we subtract 0.2514 from 0.8413 to get the proportion of people who are the probability that a randomly selected adult will have an IQ between 90 and 115. So if we subtract those two, we're going to come up with a probability. So we've got, let's go to calculator. 0.8413. We're going to subtract 0.67 minus 0.2514, and that's going to equal 58.99%, 0.5899. So 58.99% of adults would be expected to have an IQ between 90 and 115, which also tells us that 41.01% have an IQ either below 90 or above 115. Okay. Now, intuitively, we can look at that page. Looking here. Okay. So we can look at the picture and see that it's going to be a little over 50% just by our own estimates. I've lost the page. What page was I on here? 262. Okay. So we have lots of ways of looking at, using these sorts of scores. Okay. Now we can determine the reverse. We can determine the reverse as well. We can look at the area to the left of our score, and we can use that to calculate the score. Let's look at number 9. We've got an area of 0.6, and we want to know what the z-score is. In other words, how many standard deviations away from the norm. So if we look up, go back to our table, and then look for 0.6 in as an area. Remember, the body of the table is the area. The column to the left of the table, on the left side of the table, is the z-score. So we are looking at an area of 0.6. So we know that it has to be on the positive side. We see that from the shape of the graph. So we know we're going to look at the positive side of this table. So we look at the point where we actually have 0.6. And note, it is 0.25 and then a fraction, because it is partway between 0.5987 and 0.6026. The difference between 0.5987 and 0.6026 is 0.0039. And what we want to do is look at the difference. So we've got 13 is the difference between 0.5987 and 0.60. Okay, so 13 divided by the total span of 39 is 1/3, 0.33. So we have a probability at this point, a z-score of 0.253. Okay, taking it only to 3 decimal places. That's all you can do with a table like this, is add 1 extra decimal place. So our z-score is 0.253. So it's 0.253 standard deviations above the norm. So we can calculate the z-score based on the area. Let's look down at number 11, 0.95. We want to know the z-score. It's going to be a minus because it is to the left of the mean, right? So what we want to do is find the area to the left of that x. The way we get that is to subtract 0.95 from 1. Remember, the total area under the curve is 1, normalized to 1. So we have 0.95. So x, 1 minus 0.95 is 0.05. So now we go to the z table and we look for 0.05, and that's going to come into somewhere between minus 1.7 and minus 1.6 standard deviations. If we look at where we get to 0.05, if we look at minus 1.60, we get 0.0548. If we go back up and look at minus 1.79, it's 0.3567. So we have a large span here, okay? 0.0367 is, we have to subtract that value from the next value up, which is 0.0548. If we subtract that 0.0367, we get 0.0181. And note that the difference between 0.0367 and 0.05 is going to be 0.133. So now we're going to divide 0.0133 by 0.0181. And get 0.7. So what that says to me is that the z-score is minus 1.797. In other words, just shy of 2 standard deviations, which means that it's not an unusual number, right? It's within 2 standard deviations. That makes sense? Okay. So we can use these either area or z-score to determine, to determine the other. Using area, we can determine z-score. Using z-score, we can determine area. Area is probability. Remember that. If someone says, what's the probability of a person falling in an IQ of below 120, we just look up that z-score. We've calculated z-score first, which means means we subtract the value of x from x bar, the mean, remember? And divide that by the standard deviation, S. Okay. Now, in something as big as this, we're talking about a population. So the symbols might be mu and sigma, but they're the same thing. The only difference, or the reason we use either mu or x bar is to differentiate between a sample and a population, right? And sigma versus S is population versus sample standard deviation. All right? So we can do those. So we can, again, we can do all sorts of problems like this. But what questions do you have? Okay. What other questions do you have about the use of these standard distribution tables? Remember, if you are dealing with a standard distribution, the example that we have of IQ here, clearly, if we look at our standard deviation, the mean is 0 and the standard deviation is 1, the z-score. Okay, the number of standard deviations is based on a standard deviation of 1. If we are dealing with data sets where the mean is something else, and the example of the IQ scores is 1, here the standard deviation is 15 and the mean is 100. All we have done is calculated using those set values. We have calculated a z-score. The z-score is a way of normalizing the table. Normalizing means to take it to a standard analyzable format. And of course, the format is that of the standard distribution, area equals 1, as exemplified by table A2. Right? So if we are given a set of data and we calculate a mean and a standard deviation, then we can use that to calculate the probability of a data point appearing within a certain range. That makes sense? Okay. Let's do a let's see, I just want to find need to find a data set. Um, uh, Okay, let's take an example here in the book. I'll draw this out a bit on the board to try and make a little better sense of it. I'm looking at page 273, and I'm looking at question number 25. Now you may ask, how can we deal with this? What are the numbers? And what we know actually is given to us at the top of that set of questions. Number 25 reads, the U.S. Army requires women's heights to be between 58 and 80 inches. Okay, find the percentage of women meeting the height requirement. Okay, women's heights, we look up at the top page, just above question number 21. Women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. So we're going to draw this out. And again, what we have is a mean of 63.6 inches, and the standard deviation is 2.5 inches. Okay? So the question is, if the requiring of the U.S. Army requires women's height to be between 58 and 80 inches. We know that the standard deviation is 2.5. So we've got 63.6 inches. Remember the z-score, number of standard deviations, is going to be x bar minus x over the standard deviation. And the difference between the value of x and the mean divided by the standard deviation. So we have 63.6 inches, and the Army is requiring them to be 58 inches. 58 inches. Okay, 0.6, 8 from 13 is 5. 5.6 inches, okay? So we now have minus 5 point, we're looking at x bar, or excuse me, x minus x bar, I'm sorry. The difference between the number and the mean. Okay, so we've got minus 5.6 over 2.5 is going to be a z-score. Okay, so what we have is, let me grab my phone again. We're going to divide that out. 5.6 divided by 2.5 So z-score is going to be minus 2.24. Okay. Now our other number was somewhat higher. It was 80. It was 80 inches. Okay. So we have, down over here, we have 58 inches, and up here we have 80 inches. Okay. So now we have 80 minus 63.6 over 2.5. Okay, 80 minus 63.6 is 15.4. No, 16.4. Okay. Divided by 2.5. Okay. 6.56 is our z-score. Okay. So what we have is, now if we redraw this graph and look up the z-scores, a z-score of minus 2.24 is 0.125. So if we redraw this, think about this as, if we normalize our plot now, so that we can use the z-score. So this is a z-score or an area here to the left of 2.24. I said 0.0125. That's the area there. And the area above 80 is 0.9999 because it's beyond 3.5 standard deviations. So that means that 0.9999 minus 0.0125, 4789. So 98.74% of women are going to fall into the Army's height requirements. Okay. That is one of the criteria, obviously, that the military uses. So the question now, going back to what page we're on. 272. So find the percentage of women meeting the height requirement. Are many women being denied because they're too short or too tall? Well, I have to say that when 98.74% are being included, the answer to that is no. Far less than 5% are being denied. So that's one. Number two, if they change the height requirements so that all women are eligible except the shortest 1% and the tallest 2%, what are the height requirements? Well, here we have to go through and look again at our range. Normally distributed with a mean of 1%. So what we want to do is look at now what happens if we go back to our Z table and look for 1%. In other words, 0.01. And that's going to be, we're going to round things off at this point. Because there's a wide range here. Okay, so a z-score of minus 2.3. That's the 1%. Right? We're going to round it off. Minus 2.3 is 0.0107. Minus 249 is 0.0084. Or rather, wait a minute, is, if we want 1%, okay, excuse me, minus 2 point, I'm just going to call it 33. So a z-score of minus 2.33. Right? Now, we had minus 2.24. Okay. So we've got minus 2.33. So standard deviation, we can calculate that. Okay. If z equals 2.33, what is x? Right? Minus 2.33, what is x? Well, if we look over here, the difference is if we multiply z times 2.5, we get the difference between the mean and x, right? Look up here at our formula. Z equals x minus x bar divided by s. If we multiply by s, then we have the difference between the two scores. Okay, so 2.33 times 2.5 is 5.83. 5.8, we're going to round it off. So x minus x bar is minus 5.83. 5.8. So what we have is if we then subtract that from the mean, 63.6 minus 5.8, we get 0.6. 6 from 13 is 7. And 57.6. So we actually would increase the number of people at the lower end by reducing 58%, 58 to 57.6 inches. So let's look at the top 2%. So we want to look for 0.98 over on the z-scale, positive z-scale. If we interpolate that, it becomes 2.05, we call it 5, 2.055. Okay. That's going to be my z-score. So over here on the positive side, z equals 2.055. We multiply that by 2.5. We're going to get we get 5.1 inches. Okay. Now, if we add that to our mean, okay, 63.6, we get 7, we get 8, 68.7. Okay. So now we have cut out everyone between 68.7 and 80 inches tall. So we've cut out a huge proportion. So by tightening these things to these percentages, we have really narrowed the field. Now we have taken out more of our population, right? Makes sense? So we've taken out 3%. We've gone from 98.74% to 97%. So we've reduced it. So that's another method of looking at these data. And again, we normalized it by simply dividing the difference between X and X bar by the standard deviation. That immediately takes us down to being able to use this table. That's the value of the z-score. It normalizes the data. Make sense? So there's several of these kinds of problems that we can look at. And I think that's gonna set things up. Okay. Now, let's go ahead and take one more break, and then we'll come back and discuss a couple of other things. All right? Yeah, it does help to draw them out. I find that visual helps me too, quite a bit. Okay. I'd like to, do you have any questions about what we've been talking about so far with chapter 6? Okay, so this week there is assessment 4, and then there's a final exam. Okay, so assessment 4 actually is sort of a pre-final. You'll find a number of questions on there that we've seen before. But I'd like to go back and talk about conditional probabilities. Okay, do you remember that term from reading chapter 4, conditional probabilities? Okay, conditional probabilities are when the outcome can be influenced by previous events. Okay, so let's just take a look at a couple of possibilities. One of them, we looked at. Let's just take a look at page 164 of your text. On page 164, there's a question about quality control in manufacturing. Now, this holds whether we're talking about medical products or anything else. Okay, but here we have a batch of 100,000 heart pacemakers, which includes 99,950 that are good and 50 that are bad, are defective. If we randomly select 2 of the samples then what is the probability that both of them will be good? Well, the calculation actually is fairly easy. There are 99,950 chances out of 100,000 that your first choice will be good. Okay, so now we have taken out a good one and we've taken out one from the sample. We have not replaced it with another sample. So when we pull the second one, there are 949 chances out of 99,999 that we'll have a good one. And using the multiplication rule, in other words, the chance of two events occurring is the product of the chance of each of the chances. So we've got, basically we come up with a probability if you only take two samples of 99.9% that both of them will look good. This is one of the reasons that in large manufacturing runs, we don't take small samples for analysis. We want to have something that can give us a probability that we will find defects if they are above a certain level of likelihood. In this case, if we've got 50 out of 100,000, we have a very small probability of any one of them being defective. So when we have this kind of thing, we have to take larger samples. Now, there is a rule that says that if your sample is less than 5% of the total possible samples, then we can treat each selection as having the same probability. Okay. If we were to, in this example, we're talking about taking 20 pacemakers. What's the probability each will be good? We're using the logic of only taking two. Then we have each step going down 99,950 over 100,000 times 99,949 over 99,999, 99 point out of 99,948 over 99,998, etc., all the way down to 99,931 divided by 99,981. This is a cumbersome calculation. We can easily set that up on Excel. But the point here is that we can do that, we can run that out, and if we round it to 3 decimal places, we get, you can run it out if you want, but you can take my word for it. We can get the same answer by just treating 20 iterations of 99,950 divided by 100,000. In other words, we raise that to the 20th power. And we can do that easily on either Excel or our calculators. But in that case, we get 99% likelihood that any 2 randomly chosen pacemakers will be good. And if we carry out the longer calculation and round it off, it'll be the same. Okay. So there is a rule about that. But the sampling frequency of our QA program is governed by the expected default rate, the expected defect rate in the manufacturer. Now, in order to get up to a meaningful sample, we would have to pull out 5,000 pacemakers to get up above 5%. So when our defect rate is expected to be below 5%, and we have large manufacturing runs. If we have small manufacturing runs, that's a different story. Again, smaller samples give us a higher probability of finding defects. Okay, but so this is why things slip through the cracks. Why there are still computers that don't work when we turn them on after we get them home. Why there are still, batteries that come out of the pack with no charge. Because there is a certain level of failure that is not detectable by affordable QA procedures. You can't take 5,000 pacemakers and test them. First off, there's no time or personnel. And second off, that's a significant chunk of your manufacturing run. Would it give you a better probability of finding defective, at determining a defect rate? Probably. Is it worth doing? It's probably cheaper just to replace one that doesn't work. And that's why before a pacemaker is installed, they actually test it. They're as close to 100% as they're going to get. Yeah. If they, yeah. Right. Yeah. If we look at, at a defect rate of 50 out of 100,000, that is a minute number. That is 5 out of 10,000, which is a pretty small percentage, usually well within acceptable error limits in manufacturing. So again, this is a method that we employ a statistical analysis on. Okay. If we accidentally find a defective one, well, obviously we throw it away or rework it. But we are willing, most people are willing to accept a certain level of defect. We think that, no, I'm not willing to accept that. If I buy a computer, it's supposed to work. Yes, it is. But that's why you have replacement, why you have automatic replacement if it doesn't work. That's why you take it back. That's why if you go to pick up a car and it's delivered to you, somebody has actually found out whether it'll start, whether it'll drive, or whether there's obvious defects. But minor defects, they can't catch. If there's a bolt loose on the engine mounting, they're not likely to catch that. Okay. Might not catch a thing, right? Right. Yeah, I think when I picked up my Subaru, yeah, we had to have it ordered because we wanted a different color than they had on the lot. So when we picked it up, there were less than 20 miles on the car. We almost drove further getting home than the car started with. So, that does happen. So the application rule is something that we basically do. It's really the basis for a lot of what we've done in terms of looking at statistical, at the statistics for getting like a roll of the die. There where the outcomes are equally likely, we can have an intuitive feeling. As I said before, rolling one die, you have a 1 in 6 chance of turning up a 1. Now you might roll 6 ones in a row. The probability of doing that is a 6th times a 6th, etc., up to 6 times. Okay, so it's pretty small. Okay. Is it possible? Yes. If it can happen statistically, it will in enough tries. Okay. So there is there is a process we call, using sample means as a way to estimate the mean. So if we were to roll a die 6 times and calculate, how many times a 1 came up, okay, and record that, and do this, say, 10,000 times, we'd get a distribution from perhaps 6 ones, a range of no ones at all in 6 rolls, to 6 ones in 6 rolls. And if we plotted that out, it would turn into probably a normal distribution centered on 1/6, 1 time in 6, 1 on a roll, on a set of 6. So what we have to do, we can use that. We can do a number of runs and get an idea and use that as a mean, to say doing several different trials. Maybe we do this 5 or 6 times and we get an average of, say, 1.5 ones. We may not get exactly 1. We may have exactly 1 on some. We may have none. We may have 3. Who knows? If we do this enough, as I say, we could use the mean of means as an estimate of the mean of a population. Does that make sense? But it's an estimate. It's not going to be the intuitive mean. The odds of rolling, and if we roll dice and we look at a single die, there are 3 odd possible results, 1, 3, and 5, and 3 even possible results, 2, 4, and 6. Again, intuitively, we ought to come up with 3 even and 3 odd each time. But each trial is going to be a little different. We may come up with, in one series, 2.5 on average as a mean of odd numbers. But in another trial, we may get 3.5. So we can take, so if we do enough of these and we define our parameters right, we can use the mean of what we call the mean of the means, the mean of different trials, to estimate a population mean. Okay. So let's look at another variation on this conditional probability. And one of them has to do with, at the very beginning of chapter 4, they present polygraph results. If we look on page 137, there's a table, results from experiments with polygraph instruments. Okay. When you ask a question of a subject taking a polygraph, they're either going to tell you the truth or they're going to tell you a falsehood. Okay. Yes or no, lie or truth. You have two other possibilities that can occur. One of which is the polygraph reads that it was telling that the subject was telling the truth, or the polygraph says that the subject's lying. But there are false positives and negatives. So some of the people taking a polygraph and getting a positive result will have actually lied. And some of the people getting a negative result will have actually told the truth. So we look at these data and we ask a couple of questions. Okay, we can look at the total number of tests. And in this particular case, we had a total number of tests of 47 positive results and 41 negative results for a total of 88 tests. Okay. So we can say, what is the probability that a subject told the truth given that he had a positive result, meaning that the lie detector said that it was a negative, that he lied. What is the probability of a positive result given that the patient, or the given, what is the probability of a false positive? And the reason that we ask that question is we are looking at the number of people who tested negative, in other words, tested as lying, but who did not. So what we do is we look at the total number of positive results, which in this case was 57. 15 of them were false. So that's 15 out of 57, not 15 out of the total 88. So we have to parse the data. We can look at this, and so now we have 15 out of 57, which is close to 25%, which makes you be suspicious of polygraphs, right? It's one of the biggest problems. It's one of the reasons that polygraph experts will ask the same question a number of different ways, because we'll react differently. There are people that can lie without showing any evidence of doing so. Okay. If we look at negative, in other words, the subject did not lie, we've got 9 that were false negatives. In other words, they actually lied, and it said they didn't. So the false negative rate is 9 out of 41 in this study. In other words, about 1 in 4.5, yeah. So we have to look at this as an indicator that lie detectors, polygraphs, may or may not be accurate, but we have to take into account the likelihood of false positives and false negatives when interpreting the result. If we look, there was questions about there's questions about let's take a look at another possibility here, and I want to look at let's see, we looked at those. One of the questions that we have here is, there's lots of we have to look at what the sample is. Questions that you've had in the homework had to do with things like smokers, heavy smokers, light smokers, or non-smokers. Okay, women and men. A question like, what is a random choice? What is the probability that a choice would be a non-smoker given that it was a woman? So what we have to do is look first at the total number of women, because it's given that they're women. We've just eliminated the men. So if there were 900 subjects and 400 were women and 500 men, then now our universe has been narrowed from 900 to 400. When we say given that, it means that the complement of that, the non-women, are excluded from the analysis. Okay? And if we know that maybe 50 of those women were non-smokers, there's the probability now of 50 out of 400, or 1/8, that you're going to have, or 12.5%, that your choice will be a non-smoker. Okay? So when you are given a conditional probability, look at that. Look at if it says, given that a person is above a certain age. Okay? That means that you have to rule out everyone below a certain age, because the complement of above a certain age is below that age. Or looking at probabilities of given a situation here, if we were looking at say speeders, people speeding down the road, we measure their speed and we classify it, we list that, what do the police normally do? Well, they normally ignore at least 5 over the limit. Okay, at least to that level. Some of them will ignore more. But let's just say, what are the proportion of speeders going more than 5 above the limit? So we have to look then at the total number of speeders, and then the total number of speeders going above that limit, and that's how we calculate our proportion. So a random speeder, we'd be looking at that as a random speeder would be, what would be the probability that some randomly chosen speeder was going above 5 miles over the limit. So if the limit was 65, what's the chance that they were going above 70? We'd have to eliminate. Remember, we are looking at the number of people going, the total number in that case of speeders, but we're looking at only those above a certain level, not at, but above. So we have to read our questions carefully. Okay? What time is it? It's time to go. Sorry. Then we'll meet back here on Wednesday, and I would like to just go over all of the concepts that we've covered in the class as preparation for your final exam. All right? So if you have any homework to turn in, please do. I need to have it. I need to get it graded. April, are you with us? I don't think she is.